Hello, this is question 3 from the 2019 MAT. Let A, B, M be positive numbers. A is between 0 and B. In the diagram below, I'll sketch the parabola with that equation and the line y equals mx. Line is tangential to the parabola. Right, okay. R is the region bounded by the axis, the line and the parabola, and S is that region. Right, so everything's on the picture, so we don't need any of that at all. Part 1 for C is C. Oh, okay, the upper limit of the integral. For C is greater than 0, evaluate this integral. Right, this is just standard stuff then. So we're going to have, well, xc, we'll go to cx squared over 2, and then we'll have a minus x cubed over 3. C and 0, we don't have to worry about the 0, so we're going to have half of c cubed minus a third of c cubed, so that's c cubed over 6. So, oh, there's more. Without calculation, explain why the area of region S equals that, b minus a. Yeah, well, they just moved the limits along. They just translated this parabola along to AB as the limits rather than 0c. So explain why. So if we translate the parabola in the x direction, then this will not change the area, S, and we can move the 0 and c limits to A and B. So therefore, in that case, we'd be saying that, what are we saying on that then? How are we getting the final bit? We're moving to 0 goes to A and C goes to C plus A, and that equals B. So therefore we're going to have that C equals B minus A, and then we've got this thing now, we put it into our integral, will be B minus A cubed over 6. Right, that was fine. Part 2, the line y equals mx meets the parabola tangentially as drawn in the diagram. Yeah, fair enough. Show that m is that. Right, this is another fairly standard bit of work to do here. Maybe there's going to be a twist in it. So they've got to meet there. So we've got mx is equal to x minus a, b minus x. We want one solution to this for it to be tangential. So what we're going to have on all of this then, actually I'll just expand this out here because we've got some annoying minus signs. So minus x squared minus ab plus ax plus bx. So all in all then, we're going to have, well, x squared is the only thing we've got, and I'll make that positive. That's the only x squared term we've got. Make that one positive. Then we got an m, we got a minus a and a minus b. They're our x terms. And then we got a plus ab. That has to all equal 0. We want one solution. So we want our b squared, our m minus a minus b squared, minus 4ab to equals 0 for our one solution. So m is going to be a plus b plus or minus the square root, or well, 2 lots of the square root of ab. Right. Well, what do they want us to get? Root b minus root a all squared. All right, yeah, okay, well, that is going to be that. So we've got, except we've got root b plus or minus root a all squared. So we've got two different gradients, and we want to take the negative one. So why have we got two? Oh, yeah, we've got two solutions, I suppose. Because if we keep this going, let's do a zoom out of this. So we've got our parabola, which is, you know, something like this. then we're going to have one solution when we've got a low gradient, but we'll have another one down here in quadrant 3, won't we, if we got a high gradient. So we can say the plus for solution in third quadrant, and we've got the minus in the first quadrant. Therefore M, so this is first quadrant, is going to equal root B minus root A all squared. Okay, so that's a little bit of a twist at the end then with having those two solutions, but nothing crazy. All right, new sheet up. This is the last part of the question already. Assume now that A is 1 and write B equals beta squared. Beta is greater than 1. Given that the area of R equals that, all right, so they've already told us R. Okay, show that the areas of R and S are equal when, again, just seems like an algebra question. So what do we got then? Because we've got both of these things sat here, haven't we? So S we've worked out previously is that. So that is now, well, B is beta squared. So let's put that there. Give myself a bit more space. Beta squared minus A, and A is 1. So beta squared minus 1 cubed over 6 has to be equal to, and they've given us R, haven't they? Yeah, here we go. So it's in the 2 beta plus 1 times beta minus 1 squared over 6. So clearly the 6's don't matter. So let's forget about those. And what sort of thing are we working towards? We've got a beta minus 1 squared here, because we've got a difference of 2 squares on the left-hand side, and then we just got to expand things out. So we'll write that then as beta plus 1, beta minus 1, all cubed, is equal to beta minus 1 squared. I don't know what I've written it in the, well, I do know what I've written it in the other order. I want to get these beta minus 1s together. So let's get everything to the left-hand side. Get that beta minus 1 squared on the outside, which means we're going to be left with one more beta minus 1, and then a beta plus 1 cubed is what we're going to have there. And then we're going to have a minus 2 beta minus 1. So you just have to deal with this horrible bit inside the brackets then. And then we're fine. So this is going to be beta minus 1. I'm just going to write out this bit, I think. Beta cubed plus 3 beta squared plus 3 beta plus 1. And then, actually, I will write the whole lot out. Why not? So we've got that. And then beta minus 1 squared. So all again, the stuff inside doing the big bracket. So we've got a beta to the 4 plus 3 beta cubed plus 3 beta squared plus beta minus beta cubed minus 3 beta squared minus 3 beta minus 1 minus 2 beta minus 1. So this should be it then. So we've got a beta minus 1 squared, which is our first bit. We've then got beta to the power of 4. That's the only one we've got of those. Beta cubes, we've got a 3 minus a 1. So 2 beta cubed, that works. We've done that one and that one. Beta squareds are cancelling. That's that one and that one. Betas, we got a plus 1, minus 3, minus 2. So minus 4 beta. That one, and that one. And then we got a minus 2 equals 0, which is what they want. All right, explain why there is a solution beta to this equation in the range beta's greater than 1. So if beta's greater than 1, we're not getting the solution from the first bracket. So this thing's always going to be positive. And, well, I suppose all we have to do is show that it's changed sign. So if beta equals 1, say, then we get, well, actually we get beta equal 1 when we got 0. So if beta is, well, let's look at the second bracket then. So we need the second bracket to equal 0. So when beta equals 1, second bracket is going to be what? We got 1 plus 2 is 3 minus 6 minus 3. If beta equals, actually we don't need to go up much here, even if we go 2 it's going to go positive. The second bracket is going to be 16 plus 16 minus 10. So it's already positive. I can't remember what I said now. Was that 22 or something like that? Anyway, so we've got negative, positive. So there must be a solution in the range of betas between 1 and 2. Okay, without further calculation, deduce that for any a is greater than 0, there exists b greater than a such that the area of region S equals the area of region R. Right, so any a is greater than 0. So what have we done so far? It's always the thing, isn't it? Look at what we've done so far. So we've shown that R equals S. So we've got that R equals S for a equals 1. There is a solution, but we don't know what it is. So beta is somewhere greater than 1. We've got, well, we know it's less than 2 as well, but still, we've got some solution for when a is 1. We need to show that there is a solution for any a. So suppose we just do we do a stretch? If we do a stretch, we can't translate anything because, yeah, if we just translate it, so we've got the same S, we're going to get a different straight line and it's going to change R. So we can't do a translation. So we're going to have to do a stretch. Yeah, because if we stretch it, we've got A sitting at 1, we move that to A. So we just do a stretch in the X direction. We're still going to have a tangent point. We're still going to have the straight line going through the origin. And we're still going to have the same ratio of areas. So it's going to have to be that then. So if we stretch both lines in the X direction, then the ratio of areas will be the same. So i.e. R equals S. The tangent still tangent. Tangent remains. And we can stretch from A, and we can move A to, well, A from 1 to any A is greater than 0. So we have to say something about beta. What we got then? Beta is, yeah, what are we saying about beta? Well, we know that B will still be greater than A, and we're still going to get an answer. So we'll still have the same thing, as far as I'm aware. Yeah, B is still going to be greater than A, because, yeah, we're still stretching for any A. Right, I'll run out of space now. So yeah, and I'm just wondering out as the usual problem of how to put this into words. So B will still be greater than A because A is at 1. We know we've got a solution here for beta being greater than 1. So B is still greater than 1, which is what we want, because we've got A sat at 1 in this particular example. So that's okay. And so we'll go with that. Well, yeah, and B is still greater than A. Is there anything else to say? I don't think there's anything else to say. We are just doing that stretch. Yeah, I mean, that's sort of dropped through okay, that question. It was pretty much a straight algebra question, really. I mean, we had to do a simple integral at the beginning, and then this was just doing algebra. This was just doing algebra. and then a couple of little bits at the end. So yeah, unusual for question 3. Quite often in question 3 you get horrible like function questions and stuff, but that one was a bit different to normal. Yeah, not that bad really.